All right, so lesson 7.2 today, properties of exponential functions. So like I said, we'll be dealing a lot with transformation rules that we've looked at throughout the year, just in the context of exponential functions. So a lot of this stuff is going to be a review, just like I said, in a new context. So our parent function would be y equals b to the power of x. And then this is what we looked at yesterday. Y equals a times b to the x. So a is a stretch or a compression, depending on the absolute value of a. If the absolute value of a is greater than 1, you have a stretch. If it's between 0 and 1, you have a compression. And then we have the translations as well. So if we have x minus h, that's going to be a left or right, and then the plus k is up or down, right? So nothing new there, but again, sometimes it just looks different in a new context, like with an exponential function. So with that, we'll go ahead and work example 5. It says how does the graph of y equals 4 to the power of x plus 2 compare to the graph of the parent function y equals 4 to the x. All right, so what we have on the graph there is y equals 4 to the x. Okay, so you actually have, I think, one on your homework where you have to figure out the equation based on the graph. So just some things you can look at are, we know this tells us a, so a equals 1 here. And then from there, if a equals 1, it's a little, it's pretty easy. So you could look at what does 1 go to, right? So 1 goes to 4 here. So then you're thinking, what to the first power equals 4, right? So that would tell you it's y equals 4 to the power of x. But that may be one we look at tomorrow during our review day. Okay. Anyways, that's the graph of y equals 4 to the power of x, if you want to label it. And so how does this other one compare, right? So this would be, this is of the form f of x plus 2, okay? And so that's a left or right, so that's going to be, remember, counterintuitive, the opposite of what you would think, so this would be left 2. So just say it shifted or translated left 2 units. All right, and then we'll sketch a graph. We could use our graphing calculator here, or we could just, take all the points we see there and shift them 2 to the left. So that's just what we'll do. So instead of 0 goes to 1, we'll have -2 goes to 1. And instead of 1 goes to 4, we'll have -1 goes to 4. Okay, and then just trying to kind of trace the curve. And remember, when you are tracing that curve, that x-axis acts as what we said yesterday was an asymptote, so it never goes across that, okay, on these exponential functions. All right, so moving on to the next one, example 6. How does the graph of 4 to the power of x minus 2 compare to the parent function? Yes? Yeah? All right. Anybody know how to answer the next question, without looking at a graphing calculator or anything? If we're looking at y equals 4 to the x, take away 2, how's that compare to its parent function, 4 to the power of x? Gretchen? It goes down 2, right? So this is of the form f of x minus 2. So if it's outside of the input variable, it's an up or down. So this would be a down 2. So this would be shifted down 2 units. Bless you. And again, we can just develop that graph based on its parent function. So if we shift everything down 2, instead of 0 goes to 1, we'd have 0 goes to -1. And instead of 1 goes to 4, we'd have 1 goes to 2. What would be my asymptote in this case? Obviously, we're below the x-axis with those points. Does anybody know what my line I would never cross would be in this case, Eli? Yeah, it'd be y equals -2. Okay, you may want to label that there. All right, so moving on. Now we'll get into some more complex examples. Now, if any of these were like a test question, so in example 7, it says, state what the parent function is, and then describe the graph of each function is a transformation of the parent function. So, or as a transformation. If this were on the test, you could definitely, kind of look at your graphs, and we may look at one on Desmos just to see, because there is kind of a visual element to this, but I really want us to focus on just the rules, just the rule itself, okay, and try to take what we've learned in the past about transformations and apply it to this. All right, so your parent function, again, if we look back at the definition of that, it's just y equals the base to the power of x, okay? So we can go ahead and name the parent function for all these. So for A, it would be y equals 1/3 to the power of x. B, the parent function would be y equals 3 to the x. And why don't you go ahead and do that for C and D? Just list the parent function. We'll do the transformations part together, at least on A and B. All right, so for C, our parent function would be y equals 5 to the x. And then on D, y equals 2 to the x. Okay? Any questions about naming the parent function? Would it be what? No. Which one are we looking at? No, so the parent function is always, so that -6 is that's a transformation. So the parent function is always in this form right here. Y equals some number to the power of x. Okay, does that make sense? All right. Everything else is considered a transformation of that. Okay. So let's go ahead and look at A and B, and again, just kind of on an algebraic level. All right. So visually, as far as the equation goes, or the function rule goes, what's different from the parent function? Obviously, it's multiplied by 2, and the -6, right? So we have 2 transformations that we need to talk about. Usually we just go from left to right, but that's not really important. So the first one, the 2, would be anybody know? Stretch, very good. So that's a stretch. And I like to just say where A equals 2. All right, and then what about the other one? What would that be? You can just blurt it out if you know it. What is it? Yeah, down 6. Very good. Thank you, Gretchen. Down 6. And if we're looking at the formulas, up or down, whoops, up or down, I think they usually call that K. There we go. Yeah, so K for up or down. So we could say K equals -6, if that makes sense. All right, so that's all we're doing here. And again, if this were a test question and you would want to verify that, think about what you could do. And we may do this at the end of this example. but you could type in y equals 1/3 to the x, and then you could type in y equals 2 times 1/3 to the x minus 6, and just see if, is it stretched out and does it move down 6, right? That's an easy check, especially if you're more of a visual person. All right, so on the next one, we want to, kind of looks like there are 2 things that are different, but we actually want to treat it like there's 3. So you could almost think of this one as, you may want to rewrite it this way. We could almost think of it as y equals -1 times 1/4 times 3 to the power of x plus 5. Okay, so that negative part, we treat that as something different. Okay, so we have that. We have the 1/4, and we have the plus 5. That's with the x. So we're going to talk about 3 things here. All right, so the negative, if I take negative times f of x, what's that? A reflection. Which axis would it be? X-axis. Very good. Okay, so we can say we reflect over or across x-axis, because it's of the form negative f of x. All right, the 1/4 stretch or a compression there. Compression. Okay, so compression where a equals 1/4. And then the third thing, the last thing, that would be left 5 or right 5? Left. So left 5 units, because h equals, looks like 5, but actually h is -5. All right, so that's basically what I want you to do over the next few minutes with C and D. Well, first, before you try that, does anybody have any questions? Gretchen? So that's a good question. So the question was, if it's a reflection, does that change it from growth to decay? And we actually just treat it differently, right? We only talk about growth or decay for those ones that are above the x-axis. Okay, once it's reflected, it's just a whole different thing. We don't really use the term growth or decay, but that's a very good question. Okay. All right, so you guys go ahead and try C. Just try to name those transformations. If you're not very good at this, maybe work with a neighbor, and we'll talk about it in about 3 minutes. And if you have a little bit of extra time on these, maybe try to look at them visually, either on your compare them to their parent function, either on Desmos or your graphing calculator. And there you can start to sometimes you gotta go a little bit past what I'm asking you to do, right? So again, if either of these were a test question, right, how could we kind of check this? How could we be very confident in our answer, right? Because I think a lot of you guys are looking for strategies like that. Sometimes you got to be a little bit creative. All right, it looks like a lot of you guys are done, so I'm going to go ahead and maybe make that more like a 2-minute deal. So good job, way to work through them. Before I ask you for help on these, so on this last example, I went ahead and I typed in the last example we had done together. I typed in the parent function, and then I typed in the the other one with the transformations, y equals -1/4 times 3 to the power of x plus 5, which that's what it looks like. And then I can quickly just look at a graph and compare, right? So we can, the easiest thing to see is that it's reflected across the x-axis, right? Because it's upside down. We also said that it's going to be shifted to the what do we say, left 5, right? It's clearly looks to be shifted to the left, which is a little bit tougher to tell, without the with the reflection there. And then we also said that it is a vertical compression. And so that's the hardest thing to tell visually, but you can at least, while it's not a perfect way to check your answer, it at least gives you some validation that your answer is correct. Okay. All right. So looking at C, we have 2 transformations from the parent function. So if you get called on, I'd like you to try to list both if you can. All right, Ms. Kraft, what transformations did you come up with? Okay, so that was D. All right, so reflect over x-axis. That's correct, and up 1 is also correct. So those were our transformations on example D. Good job, Ms. Kraft. And then looking at C, what are our 2 transformations there? Michaela, what'd you come up with on C? Right 6, up 8. That's right. That's an example of one right there. C is really easy to check, right? So if it's up down, up down left right, those are a little bit easier to check. Okay, so anywho, let's go ahead and move on to the back side if nobody has any questions and talk about this natural base exponentials, base E. So the base E is something that we'll refer back to once we get into logarithms. So that's the next lesson, 7.3. For now, you can just know that it's some irrational number. So kind of like pi, never terminates, never repeats. So pi is like, we estimate that at 3.14. E is estimated to be about 2.72. All right. So don't worry about a whole lot right now, like why we care about it. But it says you can evaluate powers of E in your calculator by doing this. Okay, so e to the x. So where is E? We can see that it's right above the natural log button. So all that's spelled out for us. So just practicing using our calculator here, not really understanding what E is or why we care about it, just finding it on our calculator, right? So how would I punch in E to the 4th? So go back here. To bring up E, you do second, and then LN, right? And it said on the, I think it said on the notes you have to hit the caret key, but clearly here you can see we don't. It automatically brings up the exponent on this calculator. So we wanted E to the 4th, so I'm just going to type it in. And so on these, I think on your homework it says go 4 decimal places, so we'll estimate that to be 54.5982. So 54.5982. All right, so not a whole lot to this, just again, practicing using your calculator here. So go ahead and try to do the next couple, and we'll compare at the end after the timer. So e to the -2 would equal what? E to the 3/4 would equal what? All right, so e to the -2 is about 0.1353, and then e to the 3/4, or e to the 0.75, either way, is going to be 2.117. All right, so anybody have any questions on using the base e? Just find it on your calculator. Everybody got that? I'm sure it's on Desmos too somewhere, but I couldn't tell you exactly where. Probably under functions. If you look there, if anybody finds that, you can just let us know. All right, so why do we care about it? For now, it's another form of exponential growth. So you know, exponential growth, we have modeled if it's compounded, you know, a normal amount of times, monthly, yearly, biannually, whatever. We use that, you know, the formula in our last notes. If it's compounded continuously, which is you know, it doesn't really happen in real life. It's just kind of a theoretical, mathematical kind of idea. But if it's compounded continuously, this is the formula we use. Okay. What's kind of neat is to you know, take a scenario, so like same principal, same interest rate, and then compare it. What if it's, you know, compounded monthly versus compounded yearly versus compounded continuously? Like how much of a difference does that make? That's stuff we can look at down the road, but for now we're just going to practice using this new formula. So same kind of variables, all right? So a of t is your output variable still. Instead of little a, we use p for the initial amount, your starting value. R is still the same. You want that as a decimal. And then t is still time in years, okay? All right, so example 9 says, suppose you won a contest at the start of 9th grade that deposited $3,000 in an account that pays 5% interest compounded continuously. So this is what you would look for on a test to know which formula do I use. And then about how much when you graduate in 8 years. Okay. So again, compounded continuously tells me that I'm going to use this formula we haven't used before. A of t equals p times e to the power of rt. All right, so then we can sub in what we have, right? So P is going to be our 3,000. R is going to equal 0.05. Remember to change that to a decimal. And T in this case is going to be 8. All right, so then if we sub everything in, we are going to find A of 8, which would be 3,000 times E to the power of 0.05 times 8. Okay, so then we just try to type that in correctly, just how we see it. So 3,000 And then second ln to pull up my e. So 3000 e to the power of, and I'm just going to type 0.05 times 8. And we get, going to round to the nearest cent here, 4475.47. And I always kind of think, is this feasible, right? Is it feasible that I would, get about $1,500 in interest over 8 years? And, that is in the feasible range. So, because it's possible you type something in wrong on these. All right, anyways, try the next one. This one's more straightforward, so just practicing using that same formula. Where the principal on the next one is 600, interest rate's 4.5% times 5 years. All right, so last thing, what we need to type in our calculator is right there. So 600 e to the power of whatever 0.045 times 5 is. So that rounded to the nearest cent, Mr. Fogel, would be what? What do I get when I type this into my calculator? Mr. Fogel. All right, 751. What? What's the change? All right, there we go. So we will let the record reflect that Mr. Fogel got that right. 751.39. All right, so I'm going to go ahead and stop the recording. That'll be 7-2, and post your all's homework. If you want to get started, you can.